Chapter 1, slides 67 to 86. We're now ready to look at physical properties for small molecules, and we're going to be using what we've just learned about dipole moments and structure geometry for given molecules in order to make these judgments on qualitatively on how to compare different molecules' boiling points, melting points, and solubility. In order to do this, we have to look at the attractive nature between molecules now. So what we're doing is we're looking at, say, molecule 1 and another molecule, and we're trying to understand how attracted they are to one another. Okay, and it's important to understand that molecules of the same variety, so one molecule of water and another molecule of water, can be attracted to each other or not very attracted to each other. Depends when you can compare molecules of the same or two different molecules. Okay, so that the molecules you're comparing don't always have to be the same, and they don't always have to be different. They can you have the opportunity to decide what you want to compare. But you take two molecules, whether the same molecule or different, and you look at how attracted they are to one another. This will give you an idea as to how to extrapolate or hypothesize about physical properties. In order to do that, we have to understand something about intermolecular forces, and that's really just the attractive nature between the two molecules indicated. Once you understand their attractive forces, you can start predicting things like their boiling points and melting points and solubilities relative to one another. Now, there are three different kinds of intermolecular forces I want to focus on, and I want you to always look for them in this order. Number 1 is called hydrogen bonding interaction. The second one are dipole forces. And the third are London dispersion forces. So we're going to start with hydrogen bonding. Hydrogen bonding forces, I'm going to add forces here, occur between molecules that have hydrogen not on carbon. So I'm not talking about hydrogens on carbon, because if you remember, the dipole between a hydrogen and a carbon is negligible. So the hydrogens you're looking for are hydrogens on heteroatoms. Organic chemists call anything except carbon a heteroatom. It's like, oh, something else, something other, right? Having it on carbon is not a heteroatom, right? It's the atom we're always focused on. So it's some other atom. So when hydrogen, which as we know is far left on the periodic table, when you partner that hydrogen, but not carbon, with anything over on the right-hand side, then you're going to get a real big difference in the dipole of that bond. That makes the hydrogen very electropositive. You basically just want a hydrogen on some other atom that's very electronegative, which isn't going to be carbon, making that hydrogen very electropositive. Okay, when you have that instance, the molecule containing that hydrogen, which is very electropositive, will be attracted to another molecule that has some electronegative nature to it. So there's going to be an attraction, a force between those two that attracts them close to one another. Because the dipole is so severe between a hydrogen, which is the most electropositive you can get, right? It's tiny and it's got no electron density to it. It's actually kind of a subclass of dipole interactions. It really is a dipole interaction, but it's the strongest, the most severe dipole interaction. So look for them first. Look for those hydrogens on heteroatoms that, because they're on a heteroatom, create this very strong dipole. And the stronger that differential in the electronegativity, the greater the detractive forces are, the greater the positive to negative force between the two molecules holding it together. So these are the types of forces that hold one molecule to another. If the forces are really, really, really strong at a certain temperature, then it's a solid, right? It's packing it tightly. If the forces are less so, at certain temperatures, it'll be a liquid, packed far less tightly. They're actually moving across one another. And a gas has absolutely no interaction between one molecule and another. So if you have really, really, really strong forces holding one molecule tightly to another, you need to put in energy to break it, melting point, right? To melt from solid to liquid, you need to add temperature, add heat to break those intermolecular forces. You're not breaking the bonds, you're breaking the attractive forces between the molecules. So let's go through a few of these. Hydrogen bonding has the largest effect on physical properties for organic compounds. So if you take a look, the hydrogen that we see that's on a heteroatom is right there, as indicated in yellow. Notice that for the molecule on the right, there are no hydrogens on anything but carbon. So there are no opportunities for hydrogen bonding for this molecule with another molecule of itself. The alcohol on the left, though, if I had another molecule of itself, I'm going to reorient it. So I'm basically drawing another molecule of itself. Notice that you've got the oxygen is electronegative, the hydrogen is very electropositive, and it's attracted to another molecule of itself because the electropositive hydrogen can be very attracted to the electronegative oxygen of another molecule. So there you go. That's what draws it together. That's what makes it attractive. The dimethyl ether doesn't have that attractive force with itself through hydrogen bonding. And so when you compare the boiling points, it's far easier to pull apart dimethyl ether from itself than to try and break two alcohol molecules away from each other. You need to put in more energy to do so. So the boiling point is much higher for ethanol than it is for the ether. If you have the same heteroatom, let's say nitrogen, and you introduce more opportunities for hydrogen bonding, you also see an increase in physical properties like boiling point. So if I have trimethylamine, notice that there is no hydrogen bonding opportunities for this molecule with another molecule of itself. So if you look at the boiling point, it's pretty low. It doesn't take much to rip one of these molecules attractively apart from another. If I switch to ethylmethylamine, notice that there's a hydrogen on the nitrogen now. That creates the opportunity for hydrogen bonding with another molecule of itself. Therefore, the boiling point has done a huge increase. Now it's 37 degrees, right? It's a pretty big jump. Staying with nitrogen now, but increasing the number of opportunities for hydrogen bonding also increases the attractive forces between the two molecules, and you see that there is an increase in boiling point. Now understand, you are not breaking bonds. That is not happening. You're dealing with multiple molecules now, and you're just trying to pull apart the molecules, not break bonds. That's why I hate the word hydrogen bonding, because it's not a bond. It's an attractive force between molecules. What happens when you compare heteroatom to a different heteroatom? So in one case here, you have the alcohol that we just looked at, and you've got hydrogen bonding opportunity, and you've got the amine, the nitrogen, with 2 hydrogens. You'd think, oh, I got 2 hydrogens, more hydrogen bonding. But what takes over here is the fact that there's a greater difference in electronegativity between an oxygen and a hydrogen than there is between a hydrogen and a nitrogen. And as you can see from the boiling point, the difference in electronegativity, this electropositive hydrogen it's more electropositive than the one on nitrogen. And so that effect takes precedence here. And the boiling point, you can see that it's far greater to ply it apart at 78 degrees than it is to pull apart the ethylamine. Okay, the weakest of the forces is the London dispersion forces. And this is when you really just don't have a dipole at all. Take, for example, pentane. 1, 2, 3, 4, 5. It's just carbons and hydrogens. Remember, carbons and hydrogens do not have a vast difference in their electronegativity. So they're pretty much non-polar bonds. And so you just got carbon-carbon bonds, which are nonpolar covalent, and you've got carbon-hydrogen bonds, which are nonpolar covalent. And you just got a bunch of nonpolar covalent bonds. So how do these even stick together? Well, one pentane molecule is attracted to another pentane molecule very, very weakly. What happens is as these molecules, as a liquid, approach one another, right? Or as the 2 molecules approach one another, they induce a dipole. In order to not completely repel one another, they actually shift their electrons to accommodate one another. So as they approach, they shift their electron density mildly in order to create surfaces that are opposite in electrostatic charge. But this is minor. It's very small. It's enough so that if you have enough of this induced dipole, you can have it be a liquid. So if you think about methane, without putting a severe amount of pressure into it, you're not going to see methane at our typical 1 atmosphere be a liquid. Ethane propane, you guys know propane, that's just 3 carbons and its hydrogens. You have to have it under pressure, right? Your propane gas tanks. Butane, 1, 2, 3, 4. Butane lighters are just mildly, they're barely hanging on to be a liquid at 1 atmosphere. Once you get to pentane, now you're talking pentane, hexanes, and so more than 5 carbons, just hydrocarbons. Now you can start seeing them as liquids, but they don't have very high boiling points because all that's holding them together are these London dispersion forces, these induced dipole moments that fleetingly attract the molecules. So the more surface area you have, the greater these forces become. And you can actually understand that relative to things like a gecko has the pads on its feet that can climb the walls. That's London dispersion forces. And his pads of his feet have a lot of surface area. And without that, and given the weight of his body, he can actually climb the wall. But these are very weak forces. So they're the last ones I need you to look for. That's like, when all else fails, you got London dispersion forces inducing dipoles to get things to be attracted to one another. You can see this phenomenon as we move from smaller carbon chains to larger carbon chains. So if you look at butane, which has 4 carbons, there's no hydrogen bonding and there's no real dipole there to speak of. You see that it's got a boiling point of 0 degrees. Once we add another carbon, so give it more surface area, we have now a boiling point of 36 degrees Celsius. Remember, room temperature is about 21 degrees or so Celsius. Hexanes, now we have 6 carbons. Now we're getting somewhere. Now the boiling point is 69 degrees Celsius. So you can use hexanes very easily in the lab without it, completely evaporating to the touch all the time. What's also interesting is looking at isomers. Just take carbon 5, take pentane. There are different constitutional isomers or orientations, right? How you connect those pieces together. Same number of carbons, same number of hydrogens. However, how they're oriented through space does have an effect on its boiling point. So if you look, pentane, which has a lot of surface area, is much harder to pull apart in liquid form than if you had 2-methylbutane, which now has branching. And so its shape you're hiding that carbon and you have a little less surface area. And so there's less forces to break one molecule from another. So the boiling point dips down. And once you put it in almost like a ball shaped, you've really minimized the surface area, and it makes it so much easier because there's less surface area to attractive forces to break. Now you're down to boiling point of 10 degrees. What about dipole-dipole? What about those dipoles where we're not talking about hydrogen? So hydrogen bonding is sort of the superior dipole-dipole. They're kind of the same construct, but dipole-dipole is when you're not talking about a hydrogen type dipole. That's all. It's a special type, right? Or you could say that there are lots of types of dipole-dipole interactions, but hydrogen bonding is one superior type to look for, okay? So dipole-dipole forces result when you have a really strong dipole moment for a molecule. So take, for instance, acetone. The carbon double bond oxygen has a dipole moment, right? We kind of looked at things like this when we were looking at dipole moments. And so you can see the oxygen has electrostatically partially negative, the carbon is partially positive, and you can kind of align these molecules, right, together so that their attractive negative is to the partial positive and partial positive is attracted to the partial negative. And they have a very strong interaction between one another. Now, take a look at the boiling points for isobutylene versus acetone I have down here at the bottom. The boiling point is negative 6.9 degrees. The boiling point increases when you go from isobutylene to acetone. Can you explain this difference? Okay, let's go back to hydrogen bonding, which, as I mentioned, is just a very, very strong example, and the one you should always look for first, for intermolecular forces. They're the strongest, and we see them a lot, but just be careful. It is not a real bond. It's an attractive force between two molecules. Okay, so I can't stress this enough. It's not a real bond. I hate the term hydrogen bonding. It should be called hydrogen interaction. They are strong because of the vast differential in electronegativities between hydrogen and a heteroatom. And you're really just looking for hydrogen on atoms like oxygen, nitrogen, chlorine, anything very electronegative. These are the types of forces that hold water together. So, if you think about it, water is a very small molecule. It doesn't have a lot of opportunity for London dispersion forces, right? Large molecules have a lot more opportunity, even in, adding to their dipoles. But water is tiny. And the only thing holding one water molecule to another water molecule is the hydrogen bonding interaction. So it's a pretty powerful force. Understand that oxygen-hydrogen has a larger electronegativity differential than nitrogen-hydrogen, so its force is greater than nitrogen-hydrogen interactions. And we see these interactions play a vast role in things like DNA. It's the reason why our DNA is in a helical shape, because what is holding one part of the molecule attracted to another part of the molecule twists them. It's so attracted that it twists the molecule so that they can be close to one another. And this interaction is seen biologically in a lot of areas, and it plays a role in shape, proteins, DNA structure. So I want you to be able to identify when a molecule can participate in hydrogen bonding. here are two problems, and I just want you to go through and see if you can rationalize which of the following isomers have different boiling points. Like, explain why you see the differential that you see. And also for the above, for acetic acid and diethyl ether, I want you to indicate if they have the opportunity for hydrogen bonding. Here's a bunch more practice for you. In number 1, you're going to state which of the following will form hydrogen bonds between its molecules. So basically what I'm asking you is, for this first one, right, draw another molecule of itself and say, can these two, right, two molecules of itself, have a hydrogen bonding interaction? Then, on the number 2, I'm asking which of the following compounds will form hydrogen bonding interactions with ethanol. Ethanol looks like this. So in the first one, you're doing, is hydrogen bonding available between the same molecules? And in the second one, you're assessing whether or not hydrogen bonding can occur between two different molecules, the molecule A, B, C, D, E, F, with ethanol. You can also ask yourself in this other practice, why do the functional group isomers of the ethers and alcohols have different boiling points? See if you can rationalize the trends that you're seeing in this comparative boiling point table. Does it make sense? Okay, melting points. Melting points, we're going to look at the same forces. The only difference here is that we have to consider packing. Melting points are looking at what temperature, what energy do I need to really pull apart a solid, two molecules that are just, instead of a liquid, liquids, the two molecules are moving across one another, but they're still attracted to each other. So you have a substance called a liquid. In melting point, we're looking at going from a solid where the two molecules are like compact, right? Tightly packed to one another. And we're heating it up enough to break the enough attractive forces so that they become a liquid and they're moving across one another. So we didn't have to consider packing in a liquid because they don't pack. They're just moving across one another. In melting, we have to consider packing. So melting point is the temperature at which a solid turns to a liquid, and it will vary about the packing. So let's take a look at this 1, 2, 3, 4 butanol versus this other butanol. So they have the same number of atoms, okay? Same number of atoms. So they're isomers of one another. Same atoms. And they also each have a hydrogen bonding opportunity. But there's a difference in their melting points. Let's rationalize first the difference in their boiling points. Okay. It is harder because it's a higher boiling point to tear apart. You have to put more energy in to pull apart this molecule from another molecule of itself. Why? Well, because you've got hydrogen bonding, right? The hydrogen of one molecule is attracted to the oxygen of the other molecule of itself, and you have lots of London dispersion forces. So that's holding it tightly together. And as you switch now from this long, lots of surface area structure to a more compact T-butyl structure on the right, you've minimized its opportunity for London dispersion forces. You've minimized its surface area, so you're making it a little easy. There's less surface area to break apart. You still have the same hydrogen bonding capability, but less surface area to deal with, so it's just a little easier. You don't have to put in as much heat. This makes sense based on what we just talked about. Okay, when I consider packing, on the other hand, Of these two, it is much easier to pack the T-butyl. Why? Well, it's less flimsy. There's less rotation and flimsiness because what's happening is that the more rotations and flimsiness you have, it's like trying to pack a big if you've boiled up some spaghetti and you have these long tails and they're all just kind of squirming, it's like you've got to like pack them in. But it's so much easier to pack things if you had like little tiny cubes, right? Then they stack and they pack a lot easier. So the easier a molecule is to pack, and the less wiggly it is, the less flimsy it is, the easier it is to pack. And the tighter it is to pack, the harder it is to pull apart. Because if you've got everything packed tightly and closely, their attractive forces are harder to pull apart, and you have to put more heat in. So that's why you're seeing a difference in the melting point between these two. It has to do with packing, and that's why you see the disparity, and you don't see the same trend, or the trend doesn't move in the same direction when you're comparing boiling point and melting point. And that's because melting point is you're dealing with solids, and you have to consider how well things can pack. The last one, which also uses intermolecular forces, is solubility. And this is where we can use that old trusty term, like dissolves like. Polar compounds basically mix well with other polar compounds. Why? Because they have strong intermolecular forces that are attracted to one another. Nonpolar compounds generally mix well with other nonpolar compounds. Why? Because they don't have strong negatives and positives, and they are just relying mostly on London dispersion forces. So in the following slides, you'll see I have some examples of this solvation process. Solvation is just a fancy term for the ability of a material to be surrounded by a solvent and interact. Intermolecular forces determine the solubility properties of organic compounds. Okay, and so in this scenario, we're looking at an ionic crystal lattice, something like NaCl. Na plus Cl minus. We're looking at an ionic salt. We know that salt dissolves in water. So ionic is about as polar as you can get. It doesn't get much more polar than a molecule, one atom being positive formally and one atom being negative formally, right? So an ionic molecule is super polar. A carbon-oxygen bond, which we know is polar with a dipole moment, is polar. So if you can identify that you have an ionic bond, right? And I already told you how to identify ionic bonds. They typically have those metals in group 1 and group 2. You're talking about a superpolar molecule. And superpolar molecules will dissolve in superpolar solvents. And water is a very polar solvent. So you can see how water can take its very electronegative oxygen and surround the formal positive charged atoms. And the very electropositive hydrogens of water will surround the anions. How about a salt like NaCl? I always like to bring it to something that you know. A salt, a strong ionic salt. There's your crystal. And a nonpolar solvent. Nonpolar solvent could be something like, I don't know, pentane. Just carbons and hydrogens. There's really nothing about pentane liquid that is very, very polar. And so they are not attracted to one another whatsoever. So they sort of stay to their own sides. And if you try to dissolve a salt into pentane, it probably is just going to sit as a clump on the bottom of your flask. How about a nonpolar solid, like a big long chain of fat, right? Some long chain. Just the only thing holding it together are London dispersion forces. And then you introduce another nonpolar solvent. Well, nonpolar to nonpolar, they're not discriminatory. They're going to just do London dispersion forces with everybody. And so they'll actually interact and dissolve into one another. How about a nonpolar solid? Again, a long greasy chain, and water. You can think about it, it doesn't even have to be a solid. Think about it like oil, right? Just a long greasy chain of carbons. And you have a polar solvent like water. Well, you already probably know from experience that oil and water don't mix. And here's why. Water is so attracted to itself. Why would it even mess with anything? There's nothing attractive about that oil. There's nothing very positive or negative on that carbon hydrogen chain. So they kind of stayed to their own sides, and you see a layer. They have two separate layers because they don't mix up. Alcohols are somewhat like water. Alcohols are when you have a carbon with an OH. So it's similar to water. Water has no carbon on it. It has an H on it, but it has an OH, just like alcohols. So they're very similar to each other. Water and alcohols. Water is almost like a type of alcohol. It just doesn't have a carbon, so it's not organic. As you increase the number of carbons off the OH, the less and less soluble in water it becomes. So small molecules can take advantage of that hydrogen bonding capability, but the longer the chain becomes, the harder it is to go into water. And so you see this phenomenon more greatly with ethers. A very small molecule ether, which has a dipole, right? So you have an ether. Because it's bent, you have a dipole. There's a dipole moment. So that dipole, the oxygen, is partially negative, and it's attracted to the hydrogen of water. But as the ethers become more and more carbon-based, you increase and increase and increase the number, you get to a point where it's so very much hydrocarbons that you lose the effect of the dipole. It's just minimal compared to the vast hydrocarbon C. And you can see that that has a role in decreasing its solubility in water. You can think about soap, for instance, or fats. So we know it's difficult to get a polar compound to mix with a nonpolar compound. And unfortunately, greases and oils and dirt that we get on our hands and body, those tend to be very oil-based or nonpolar in nature. And so it was found that if you're just trying to wash your hands with water and you're not going to use soap, oil and grease and dirt actually don't come off very well. So we want to use soap. Why? Because soap has a polar end. Look, it's ionic. It's as polar as it can get. And a very greasy, long tail, a nonpolar side chain. When you take those molecules together and they orient with their tails in and their head groups, their ionic head groups out, they create something called a micelle. This is when you see the lather, the soap, the bubbles, that's what you're doing. Those bubbles are micelles. And what those are vehicles for the oily dirt molecules to be carried away in the water, because when these micelles form, it traps the dirt and the oil, which is like the greasy tails of the soap molecule. But the head group, the polar end of the molecule, is very attracted to the water. So it allows things that aren't soluble in water to be soluble in water. It's like a vehicle. So make sure that when you wash your hands, you're sudsing them up and getting those bubbles going, because that lather is really enhancing the formation of these micelles and carrying the dirt away. It's also another reason where dry cleaning came from. Dry cleaning doesn't use water. The invention of dry cleaning came about when people realized that things like gasoline and kerosene, which are just long, greasy oil chains, took out dirt and grime from clothing and such. It was like this miracle. I mean, it has bad health effects, but they were just like, wow, this dirt and grime and grease is coming up with this kerosene, and it's because like dissolves like. And so if you avoid water and you just use solvents that are nonpolar, then you can dry clean your clothing. Okay, let's go back to that acid-base mechanism. Let's tie everything we learned together into this reaction, because I want to show you this now so that as we work towards acid-base chemistry, you'll be thinking about what we just covered. We now want to look at this molecule with its bonds, HCl. I now know that there's a dipole moment here. The hydrogen is very electronegative. The chlorine is, electropositive. The chlorine's very electronegative. And so there's this dipole moment of this linear molecule. We also are adding NaOH. And I know this is an ionic molecule because it's got sodium in it. And so it interacted with the oxygen. And the oxygen is not in its normal bond trend. It is only bonded to the hydrogen and has 3 lone pairs, so its overall charge is negative. And that makes sense because it's an ionic system with the sodium. So what's attracted to what? Well, the chlorine is attracted to the sodium, and the hydrogen is attracted to the oxygen. The oxygen is the one that we're going to focus on. We're thinking to ourselves, geez, of all of these systems, I've learned now that the oxygen is outside of its bond trend, right? Even though there's a dipole for HCl, the oxygen has a formal negative charge. It's outside of its bond trend, and man, it would really like to interact. It has an octet, but it would like to have an octet in its normal bond trend. So what we're going to do is we're going to use electron pushing formalism to show the story about what's happening. So what I want you to do is I want you to take that extra lone pair that the oxygen has, right? Because oxygen wants to have 2 bonds and 2 lone pairs. It's got too much to itself right now. So what it wants to do is take these 2 electrons and make a bond to the hydrogen, right? Because oxygen wants normal bond trend, 2 bonds and 2 lone pairs. And if I make a bond using that lone pair, that extra lone pair with the hydrogen, I'll actually get what I want. Now let's go look at hydrogen. Hydrogen can only have 1 bond, right? And it already has a bond. So what's going to happen? If it's going to be making a new bond, then it's got to let go of the one it already has. So I'm going to draw an arrow showing that these 2 electrons here, both of them, get dumped into, that bond breaks and those 2 electrons get dumped into the chlorine. The result is that we have an oxygen with the hydrogen. I didn't touch anything here. We've got 2 lone pairs, but I used those 2 electrons to make a hydrogen bond. Right? Those 2 electrons are now a bond shared between the oxygen and the hydrogen. So this hydrogen here is this hydrogen here. What else happened? Well, the lone pair, the bonding electrons between HCl, both of them got dumped into the chlorine. And if you recall, chlorine already had 3 lone pairs. Chlorine was happy. Chlorine had 3 lone pairs, but it got 2 more dumped into it. So now the chlorine is outside of its bond trend. It has no more bonds on it, and it has 4 lone pairs. It has more than normal. So it's got a negative charge. It gained electrons more so than it's normally comfortable with. It still has an octet, but it's negatively charged. And what else is floating around? Oh yeah, the Na plus is just floating around. It doesn't have any electrons. It doesn't have any extra to give. It's happy. Right? Why isn't the sodium doing anything? It's got a filled octet. It's fine. It gave the electron away. You do what you need to do. And it just has a new partner, NaCl. So I want this to be an entry into electron pushing formalism. When you draw an arrow has a meaning, and this red arrow that I'm drawing means take these electrons and put them here. The electrons you're taking are either a lone pair, or maybe the electrons you're taking are from a bond, like we did just now, right? Take these two electrons, this lone pair, and make a bond with the hydrogen, or take these two electrons from the bond and dump them into the chlorine. We have now come to the end of Chapter 1, which was a vast review of topics covered in general chemistry, but with the added context of how we're going to be using it in organic chemistry.